Hello, YouTube. So we're recording now. So yeah, like, as I was just saying, that we're kind of way off from the syllabus, even based on what even without the pandemic. But I think we'll actually sort of do chapter 8, our application. That actually takes less time than the theory. Sorry, I know we're doing a lot of theory, but don't worry, we're getting back to making money today. So today we'll be doing 8.1 through 8.3, and for Monday we'll actually at least start 8.4 and 8.5, if maybe not finish them. The outline for problem set 9 is due tomorrow, and the completed version is due this Monday at the end of the weekend. But again, deadlines are elastic, and I want to really encourage everybody. Oh yeah, I'm gonna type this. So everyone, come to the problem session on Friday. What is the 15th? So this is Friday, April 17th, from 10:30 to noon. Work on, and we'll get people to groups and work on whatever you need to work on to catch up. Need to work on to catch up. There's no shame in anything. If you're like, oh my God, I never did any of the problem sets, I'm gonna go back to problem set 1. I'm there for you, man. So I mean, I'll try to group people by wherever you are in the semester, wherever you are in the homework, and sort of put you in rooms together based on whatever you're working on. And there's no shame in whatever you're working on, no matter how far back you might be. And you know, any progress is progress from ahead of where you are before, and so I'm happy to accommodate that. Oh yeah, but the more important announcement, as you can see, is that exam 2 has been moved. I've sort of not partly based on sort of our not entirely entire success of our exam rehearsal last Monday, 2 days ago. I want to partly based on that, partly just based on the fact that I'm so far behind on grading exams. On grading your homework. I'm moving exam 2 to Monday, April 27th, basically where exam 3 was before. And I'm going to take advantage of that fact by having a second exam rehearsal on Monday, April 20th. More or less the same rules as 2 days ago, but hopefully it'll work a little better. And now, right. So the goal by Monday, April 27th, that we should all of us, you and I, y'all and I, should all be caught up through problem set 9. So because basically our second exam, the exam 2 will cover. So exam 2, let me put this in the margins here. Exam 2 will be on chapters 5 to 7. Or another way of putting it is problem sets 5 through 9, or the sort of relevant parts of problem sets 5 through 9. So our goal by Monday, April 27th, which is 12 days from now, is that I want all of us to be as caught up as much as possible up through problem set 9. And I hope you all saw the survey about that I sent out last night. We want everybody, I suspect the survey will come out so that the homework will be more weighted than the exam, much more weighted than any one exam, and like it'll be weighted more than the homework altogether. Be weighted with more than the final. That means everybody has to get caught up on homework, and so that does allow you some flexibility. You can sort of work on that on your own time, but hopefully that'll allow everybody to get caught up. All right, so. Right. So, are there any questions about what is to be done by what is to be done this weekend, and what is to be done especially by Monday, April 27th? Any questions? Okay, and so I'm gonna try to keep forging ahead, and for the yeah, so our attendance is a little low today, but that's okay. Hello, YouTube. Hopefully everybody's catching up on this uh, by uh, at some point, and hope right. And so yeah, and so just for what it's worth, we're starting something completely new today, chapter 8, and it's not. Ah, yes, that's those are the famous words. It's not on exam 2, and so hopefully everybody's catching up about this in late April, at least by late April sometime. Anyway, so let's go on. And for those of you who are here today, thank you and for asking questions, and let's start something new. So, all right, we'll start something new by reminding you about something old. So, how do you get better codes? So, let me remind you that a binary linear code, a binary linear bracket NKD code, script C, has length n. In other words, that means that C is, remember, so binary linear codes are subspaces of f2 to the n. And so to say that, this little symbol here means that the code C has length n, which means that C is a subspace of f2 to the n. The k, the second number that appears in the descriptor of a code, is the dimension of that code. That's the amount of information in a code word, and d represents the minimum distance. So the Hamming, as a reminder, the Hamming code H7, I think I'll write that in using pen, is a 743 code. So it's length 4, dimension length 7, dimension 4. It has minimum distance 3. And sorry, this will not make any sense until I put in this scripty H7. There we go. So the Hamming code H7 is a 743 binary linear code. Hopefully, you guys, everybody got the hang of that thing, the Hamming code H7, and so you remember that was fun, right? Like it has this magical little procedure that if you make one error in a code word, you can kind of magically correct it and get back to the code word that was intended by the transmitter, by Xavier. So remember, we have Xavier sending attempting to send code words to his friend Yolanda. So right, so that can correct. So in general, if you have a code, we showed by that Hamming distance discussion that if you have a code of a minimum distance d, that code can correct floor basically d minus 1 over 2 errors. I mean the floor of that, because you only get integers. And so here, remember, for H7, we have that this is the floor of 3 minus 1 over 2. Which is one error corrected. Well, in fact, so the abstract argument tells us that one error can be corrected, at least in some abstract sense. There is some algorithm, maybe not a great one, but there's some sort of maybe not particularly efficient algorithm that can correct one error. And the nice thing about the very specific, if you remember, the specific magical algorithm that worked for the Hamming code is a specific efficient way of correcting one error. But in general, if you have a binary linear code with a minimum distance d, then it can correct floor of d minus 1 over 2 errors, and that leads us to our sort of motivating problem, which is defined NKD codes where both k and d are large as possible given n. So let's compare the repetition codes of length n. Remember, if you've forgotten, that's a code of length n. Well, it says so in the name. It has dimension 1 because the only thing you can do is repeat the same bit n times, but it does have a minimum distance n. That's good. So that corrects a lot of errors. oops, on the floor here. The floor, it's basically n minus 1 over 2. And you usually, that's why you usually want to have, usually if you have a repetition code, you want it to be an odd repetition code, because that way that way you sort of get the most mileage out of the floor, out of this floor expression. The parity check code, and I think this is what usually why we call this the parity check code of length n plus 1. So there's sort of, in the parity check code of length n plus 1, well, it has length n plus 1. You start off with n data bits, that's the dimension of your code, and you add on 1 parity check bit, so that gives you the length n plus 1. But the minimum distance is 2. And that actually corrects, well, floor of 2 minus 1, floor of 1/2 is 0. It doesn't correct any errors, as you may remember. But it detects 1 error. So we can sort of see the extremes here. The repetition code doesn't transmit very much data, but it does correct a lot of errors. On the other hand, the parity check code transmits a lot of data, but it doesn't correct anything. So those are sort of the two extremes, and we kind of somehow are looking for something more in the middle, like the Hamming code, which somehow manages to transmit a lot of data, almost half of the transit. You barely. You sort of inflate the data you're transmitting by 75%, and you're able to correct one error per 7 transmitted bits. So these are the two extremes, and we somehow want something in the middle. Look at this thing I learned how to do. I learned how to make the box as big as possible. It's taking me 4 weeks, but I've suddenly learned how to make the box as big as possible. So we'd like to have something in the middle of these extremes. You know, something where that's more efficient than the repetition code, something where you're transmitting more actual data bits per transmitted bit, but something that corrects more, but conversely that corrects more errors than the parity check code. And it turns out that one very reasonable solution to finding at least up to a point, one very reasonable solution to finding code in between these two extremes is to use ideals. What? So all that theory that we developed about ideals turns out to be useful. Okay, so any questions about this review here? Again, the goal is to find codes that have both a relatively large K and a relatively large D. So any questions about that, or should we go on? So type Y or yes to go on, or ask a question if you have one. Okay, right. So at least everybody's sort of ready to move on, I think, or at least is neutral. All right. So let's. So again, we're starting something totally new. Let's talk about cyclic code. So so we're just sort of starting from the beginning. Except that we have to. It will be helpful for later use to know what a code is over a general field. So we want to think. So what you really want to think here, the example that you for one particular application, the thing you want to think about, that Q is equal to 2 to the E for some integer E at least one. So I mean, I think there are actually uses. There are actually sort of trinary codes, but because computers, for the most part, as far as I know, mostly work using binary. This is the case we want to think about. We want to think about we have fields, so we want to think about like maybe F8, F16, F. Well, at some point we are going to think about F64 just in a totally abstract sense. Anyway, so let Q be a prime P equals P to the R. Now, I guess nowadays I'm usually using that. I should really be consistent. Use the notation P to the EE. Perhaps be a prime power, and let FQ be the unique field of order Q. A linear code C of, oh no, actually, I don't want that. No, let's stick with P to the R, which is the same idea. So let me actually make this other thing more consistent. So we want that to be P to the R, where R is at least is an integer greater than or equal to 1. And so let FQ be the field of order Q. So a linear code of C of length n over FQ is a subspace C of FQ to the n. So it's the same idea as a binary linear code, except replace F2 with FQ. Elements or vectors of a linear code are still called code words. So that's really a definition that we saw before, but just slightly generalized in a way that now this is something new. So let C be a linear code of length n over FQ. To say that C is cyclic means that C is closed under cyclic permutation of coordinates. So what do I mean by cyclic permutation of coordinates? I mean that that means you take each coordinate and move it down one. I guess C2 is here kind of invisible, except so that's a sort of beginning of a cycle. But the one thing, the most interesting thing is that everything moves down one except the very last coordinate. What's in the very last coordinate that moves up to the top, and so that's what happens if you cyclically permute once. In a similar way, if you cyclically permute twice, we do exactly the same thing again. Right, move everything down one, except you have to invisibly think that Cn minus 2 was over here and move down to here. Here Cn minus 3 was up there and was over here somewhere and moved down here. And so you have to imagine that when you do this twice, Cn minus 2 moved once and then moved back up to the top. Cn minus 1 started down here and moved up here once and got over here. So that's what it means for a code to be cyclic. If this thing over here was a code word, then its first cyclic permutation must also be a code word. Its second cyclic permutation must be also a code word, and so on, going through all n cyclic permutations. All right, so this is I guess I should say in advance, this idea of a linear code being cyclic is a bit of a gimmick. It's slightly artificial, but it turns out to be, because of the way you can think of this algebraically, it turns out to be a very useful way of what you might say finding codes in nature, and it more as a more kind of like spiritual Zen thing. Talk about in general, man. More generally, people, I guess I should say researchers, have had success finding good codes with both that are good in terms of money making, and that have both a sort of relatively large dimension and also have high error correcting among very symmetric codes. Yeah, I think. Yeah, for the purposes of this course, I'll have to leave that as kind of a cryptic statement. Well, it turns out that there are a lot of really good codes that also happen to be very symmetric. And I think actually it's probably not true for really high dimensions. So yeah, so when n gets to like 3 million or something, and I think it maybe is sort of commonly believed among researchers that when n goes to infinity, we have really long codes. Then it may actually just be that the best codes are just kind of random junk, which is kind of disappointing, like aesthetically. But nature is the way it is. But it does, when n is sort of relatively small, when n is like 20 or 30, larger than we're going to deal with in this class, but sort of relatively small as compared to infinity. The first few really good codes actually happen to also be very symmetric. Anyway, so this is one example of a code that has a symmetry in it that you can sort of rotate around. I'm going to turn my camera on just to. Actually, I'm going to ask people if it's better in some way to turn the camera on in general. So it's a code that you can sort of rotate around in a circle. Look, I made a circle. Hi, YouTube. Hopefully that actually got captured. Now I'm going to turn my camera off again so that so there's no camera. This particular kind of code that doesn't change when you sort of rotate around in it. When you rotate its coordinates circularly or cyclically, then it turns out though that happens to produce a lot of good examples of relatively small codes. I don't know. Okay, so are there any questions about what it means to have for a code to be cyclic? Okay, so that's what a cyclic code is, and now we get to the secret. Like, why is it that this kind of slightly random property of code should be useful? It's because you can view it in the following algebraic way. So right. So let me. So the polynomial. So there's a way to. So because the sort of the gimmick here. The idea, or you can think of it as a gimmick, but it's a good gimmick. It's a gimmick that works a lot. So it's a technique. The technique is to view vectors in f2 to the n, let's say. And here, I think it's helpful to think of as I'm going to use an example where if you just understand the idea of what happens when q equals 2, that will probably be enough to understand the idea in general. Think q equals 2. So again, if you have a vector let's take n equals 5, 1, 1, 0, 1, 0. Okay, so the idea is that you can always represent a vector in this notation, which oh yeah, you may have. I don't know if you noticed that we numbered the coordinates in a kind of a strange way, c0 through cn minus 1 as opposed to c1 through cn. And the reason we're doing that is that we want to think of the polynomial notation for vectors in say f2 to the n represents the vector c0 through cn minus 1, or here 1, 1, 0, 1, 0, as the polynomial 1 plus 1x plus 0x squared plus 1x cubed plus 0x to the fourth. Yeah, it represents the vector c0 through c sub n minus 1 as the polynomial c0 through c plus c1x plus c2x squared plus yada yada up through cn minus 1 times x to the n minus 1. So I think, you know what, I think that's clear. Let me do this example again, but I'm going to use 2 different colors and maybe plan out the layout a little bit better. There we go. So I'm just going to wipe out these guys. Whoop, boop, 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 boop. There we go. Let me try that again. Yeah, so the idea is there's going to be some coefficient of some constant coefficient plus some constant coefficient of x plus some coefficient of x squared plus some coefficient of x cubed plus some coefficient of x to the fourth. And let me write in green. In green here, I'm going to copy out this 1, 1, 0, 1, 0, 1, 1, 0, 1. Oh, this is better. Yeah. 0, 1, 0. So yeah, so the point is just, it's not that complicated. The point is just that this polynomial is a very strange way of writing this vector. So does that make sense? Yeah, it's very important that that this makes sense kind of early on, as early as possible. So does this maybe not from the general description, but at least from this example, does that polynomial notation make sense? Everybody, please type yes in the chat or ask a question. Okay, good. So we're starting afresh, and that sort of helps. So it helps if everybody sort of understands that one fundamental point before we move on. Okay, so so now we think about this not just but there's one tricky point about this, which is that we think about this not as a polynomial, just a sort of polynomial in general, but a polynomial in the quotient ring, capital R, which is FQ bracket X mod X to the n minus 1. So remember, when you mod out by the ideal generated by X to the n minus 1, what you're really doing here is you're setting X to the n minus 1 equals 0. So yes, remember, when you mod out by an ideal generated by one particular polynomial, what you're really doing is you're setting that that polynomial equal to 0, or in other words, you're setting X to the n equal to 1. Right. So in this ring R, which is not just the polynomial ring, but the polynomial ring mod killing this particular ideal, we're just sort of adding the extra rule that X to the n is equal to 1. So why do we care about this polynomial notation? Well, let me show you. So why do we care about this polynomial notation? And I guess I should also add, why are we working in the quotient R and not f bracket x, and not just sort of regular polynomials? Well, the reason is, if we have some code word c of x, which is written out this way: c plus c0 plus c1 x plus c2x squared plus c3x cubed, all the way up to cn minus 1 times x to the n minus 1. Then if we multiply that by x, what do we get? We get c0 x plus c1 x squared plus c2 x cubed, all the way up to yada yada. Oh, I guess I should do the last two coordinates, plus cn minus 2 now times x to the n minus 1. Oh, plus, and here's the key point, plus cn minus 1 x to the n. Okay, well, oops, and this should be, except my one typo here. There we go. I actually fixed it. It should be n minus 1, not n plus 1. So besides that, you might say, okay, well, sure, I just bumped up all the powers of x by 1. But remember, the point of working, or sort of what does it mean to work in the quotient ring mod x to the n minus 1? Well, we're setting what's exactly happening here. Boy, it's hard to draw with a mouse, but there we go. Is that we're setting exactly that last term, x to the n, equal to 1. And so this is now equal to, now let me leave myself a little more space this time. I'm going to move this coefficient over here. This now becomes a constant, the constant coefficient. And so we get c n minus 1 plus c0 x plus c1 x squared plus c2 x cubed, summed all the way up through yada yada, up through cn minus 2 x to the n minus 1. And so I think I better insert a new page here. And so, oops. And so back in vector form, this becomes I might have to sort of scroll down a bit to Cn minus 1, C0, C1, C2, oops, all the way down to yada yada up through Cn minus 1. Oops, my bad. Cn minus 2. And so if you look at, if we now go back and compare what we were saying about oh look, there it is. That's exactly what you want. This is the first. So and in words, we might describe this as, i.e., x times c of x is the first cyclic permutation just because I now know how to, I'm just going to kill this thing. There, i.e., x times c of x is the first cyclic permutation of the original vector c of x. The original of the vector of the code word. I think of c of x as the code word c of x. Right. So if I start off again, if I start off with a code word with coordinates c0 to c, a word, a vector with coordinates c0 to c1, and I multiply by x, and I put that in polynomial form, and I multiply by x, taking x to the n equal to 1, then we get exactly the first cyclic permutation of the code word the vector, not necessarily code word, but the vector c of x. Huh. All right. So just to review where that came from. Well, when you multiply by x, everything bumps up by 1 degree. This last term becomes x to the n, which is equal to 1, and so that moves into the front. And so we get exactly the first cyclic permutation of the vector c of x that we start off with. So does everybody get the idea that multiplying by x gives you the first cyclic permutation? Say yes or ask a question, please. Okay, so there's that. Does anybody want to hazard a guess in the chat as to what happens when you multiply c of x by x squared? Actually, but don't type it yet. Let's let everybody think about this for this will take forever. 15 seconds. Okay, so somebody want to type in the chat. What do you think happens when you multiply c of x by x squared? All right, excellent. Thank you, Alexis. That's right. You get the second cyclic permutation of c of x. And so let me show you what happens, at least just in terms of vectors. So you start off with the vector c0, c1 up through cn, and you multiply by x once, and we just said that gets you this vector, with c0 over here, and cn minus 1, and cn minus 1 pops up over here, c0 through cn minus 2. And so if you multiply by x again, well, same thing works again. C0 pushes down to the third position, and the Cn minus 2 comes up to the top, and C sub n minus 1 moves over here, and this goes to C sub n minus 3. Okay. All right. So right. And so so that's what happens at each stage, and the overall effect, which is multiplying by x squared, moves everything around 2 notches. Somebody else want to take a guess take a stab as what happens when you multiply by x to the k. Go ahead and type it in the chat. Excellent. Yeah, every entry. So thank you, Rise. Every entry shifts to the right k times, exactly right. Yeah. So Kate. So let me just type in what Ryusei said in terms of polynomials. Oops, meant this to be blue writing. Oh no, I did not do this. Look, I finally figured out how to make a big box, a wide box. In polynomials, in terms of polynomials notation, every entry shifts to the right k times, but cyclically. So remember, when you sort of when you shift to the right and you go too far, you go around back to the front. And then in vector notation, equivalently, in vector notation, every coordinate, well, the original vector is permuted cyclically 8 times. Okay, so yeah, so the first thing, so again, if we take advantage of this polynomial notation, and we actually, let me pull back to full page display. So if we take advantage of polynomial notation and working in the ring, polynomials mod x to the n minus 1, then the final punchline is that we multiply. If you take some random vector c of x represented by the polynomial c of x and you multiply by x to the k, then you permute the original vector cyclically k times, or every you get sort of k shifts of this sort that we see up here with x squared. So are there any questions about this sort of first initial property of the polynomial notation? Okay, so again, the thing to remember is that multiplying by x to the k in polynomial notation corresponds to permuting your original vector cyclically k times. All right. Right. So now I would. Oh no! There's our amazing. Let's see how much space I leave here. Okay. So the main fact. Let's see if I want to get to here. Sorry, let me. I forgot how exactly I planned this out. All right. Yeah. Okay. So so this is. Sorry, I'll get to this. So the first thing I want to point out is so the punchline on this is that what that means, that one fact about multiplying by x to the k gives you gives you the cyclic permutation by k notches, means that we have suddenly, the reason that cyclic codes are interesting algebraically, the reason that we can actually use algebra to study them, is that cyclic codes are exactly ideals. And yeah, man, maybe this deserves like a cartoon. So if you understand that idea, when you understand that idea, so that's that. See, this is your sign, the sound of your mind being blown. This is your head exploding here. That was doodle worthy. Maybe that wasn't exactly a particularly worthy doodle. Yes, for those of you on YouTube who are mystified by this is a doodle of somebody's mind being blown. Okay, all right, so that mind blowing, right? So all that abstract nonsense about like ideals and quotients and whatever. What was the point of all that? Well, the point is that the cyclic codes are particularly studyable by algebra because they correspond exactly to ideals. So to be precise about it. So let C be a linear code of length n over FQ. This is really, so remember, this is just a subspace of FQ to the n. Already it's sort of of FQ to the n. This is already kind of an abstract object, but okay. Or if you like, you can always think of Q as being 2 and think of F2 to the n. So in polynomial notation, to say that C is cyclic, it means exactly that C is an ideal of that ring R that we were talking about earlier, the quotient ring of FQ bracket X mod X to the n minus 1. So not just polynomials with coefficients in FQ, but polynomials with the added relation that X to n is equal to 1. Okay, so there's two parts of this. One is to suppose that C is an ideal and of R. C is an ideal of X of FQ bracket X mod X to the n minus 1. Then we're going to show that C is a cyclic code. So the conclusion that we want to reach here is that C is scripty C is cyclic. And then the converse. So and I'll sort of spoil the punchline. The converse, that's on problem set 9. Problem 821. So that if you have a cyclic code, it must actually correspond to an ideal in this polynomial notation. So that's that. So I'm going to do one half of this, and you're going to do the other. I think I'll be honest with you. I hope that when I present this, it'll make sense, and you'll be like, okay, that sounds fine. But the time when you really learn what's going on is when you do the part yourself. Because if I do it, that might be fine. If I do it on YouTube, I hope it's faintly entertaining. Hi YouTube, gift me. Oh yeah, you can't really gift me because I didn't turn my camera on, so you can't see me waving. But okay, I hope it's faintly entertaining. But the time when you actually learn something is when you do the problem. But okay, so I'll do one half. I'll do one half of this. So suppose C is an ideal of this ring. So what does it mean? So let's review what it means to be an ideal. Oops, I don't want to do that. I want to do this. So to say that C is an ideal means two things. Actually, I was gonna do this myself, but I think it's actually a better use of time. Let me ask. Let's see if I can get some brave volunteers who haven't spoken up, haven't answered questions yet today. So can somebody? But I'll start this. 1, C is closed under one thing, and 2, C is closed under. So So if you remember does anyone remember the definition of ideal? There's two parts of it, two closure conditions. Does anyone remember either closure conditions who's not sort of typed something into the chat today? Okay, and so so let me remind you that this is the stuff in chapter 7, so it is going to be on exam 2, and you do have to know it to do the homework. But let me just say, actually, you're at home, nobody's watching you. Just look it up. You're on a computer, so go ahead and look it up on. Just go ahead and look it up in the book. The book should be easily, well, not easily, but eventually accessible to you. So go ahead and take a look at that. So what does it mean to be an ideal? Okay, great. So Nat says close under addition. That's condition 1. It's like Family Feud. Survey says, bing. Yes, an ideal must be closed under addition. I apologize if you've never seen Family Feud. The other one is a more difficult or a more subtle condition. So does anyone remember what the other condition is? Again, somebody hasn't spoken up yet today. Okay. Let me see. How should I say this? Okay. Let me put in half of this, but it's not going to be the subtle half. So C is also closed under multiplication, but it's multiplication by something, and that second part is the subtle part. So does anyone remember what C is closed under multiplication by? And actually here, yeah, for the sake of time, I'll open up to people who have replied already. So C is closed under the multiplication by what? Yeah, R multiplication by elements of R. Thank you, Nat. And I should say that C is an ideal of R. So 1, C is closed under addition, and C is closed under multiplication by elements of R. So there are other. I think if we talked about subrings, then there's a thing. I mean, we mentioned it briefly, but it's actually not that important, at least compared to ideals. So often you might have a sort of a sub thing that's closed under multiplication by itself, but now here when we say that C is an ideal, C is closed under multiplication by elements of R, which possibly contains things outside of C. It's a subset of this ring that's contained that is closed under multiplication by these outside elements as well. So any questions about the ideal, the definition of ideal? Remember, you have to have that under. You want to have that under your belt by the time of exam 2, which is in 12 days. That date is going to be firm. We're going to have it in 12 days after rehearsing one more time and giving everybody some time to get caught up, a couple weeks. So any questions about the definition of ideal? Again, our review there. Okay, so the point is, so what does it mean to be closed under multiplication by elements of R? That means that if C of X is in script DC, then and F of X is in R, then F of X times C of X is in C. That's what it means to say that C is closed under multiplication by elements of R. So let's take F of X equals just X. That means that if C of X is in C, then X times C of X is in C. other words, here I have to confess, I kind of gave myself the shorter half of this. In other words, oops. In other words, if C of x is in C, what do we just say? What did we just say that the x times C of x is? We just saw, going back up here, that C of x is the first cyclic permutation of the vector x times C of x is the first cyclic permutation of the vector C of x. So in other words, if C of x is in C, then it's then each of it. Actually, let me say it, and the same for any x to the k C of x. So in other words, if C of x is in C, then any cyclic permutation of C of x is in C, is in script C, and that is exactly the definition of what it means to be a cyclic code. A code that is what does it mean to be a cyclic code? A code that is closed under cyclic permutation. All right, so so this idea that a multiplication by x gives you cyclic permutations is gives you half of this theorem. This theorem that cyclic codes are exactly ideals in this strange ring R. So that's so like I said, that is half of. We just proved half of that theorem, and the other half, which is, I mean, the reason I'm asking you to sort of, I know this is not a proof class, but I think in order for you to get an idea of what this polynomial notation really means, and to get a handle on this going back and forth between vectors and polynomials, really, that's what I'm asking you. That's what I'm asking you to prove this in the homework. Proving the other half of this, the converse, that if you have a cyclic code, then it must actually be correspond to an ideal of this ring capital R. And I think when you do, then that'll help you get a better understanding of what the polynomial notation is, and sort of what it means to be closed under multiplication by permutations, by polynomials. Okay, so are there any questions so far? But for now, are there any questions about the one half of the proof that I just did, as opposed to the other half of the proof that I'm going to have you do? Okay, so all right, let's that's actually the content of 8.2, that cyclic codes are ideals. The definition of cyclic codes and the fact that cyclic codes correspond to ideals of this strange little ring here. Okay, so let's go on to 8.3. Yeah, so I think I should have noted here, this is now section 8.3. So let me blow this back up so you can see a little better, or at least maybe so I can see a little better. So we start with the following theorem, whose proof I'm not going to go into. There's a more detailed proof in the book, but I think all you just need to know is the results, and maybe just some idea about how the proof goes. So let's fix n. So let n be constant, and let script DC. Oh yes, I should say what I keep saying, script word script DC. So this fancy looking C here is supposed to be a C written in cursive. And so this is, and so I'm gonna, I just realized I've been saying this the whole time today, but I haven't really sort of explained. So this is like script C. So this is, I think, the sort of standard way of saying that is that this is script C, and because I'm immature, like I have the emotional age of, I'm emotional like some sort of 14-year-old. I call this script C. Okay, so script C, let script C be a non-zero cyclic code of length n over FQ. In other words, let suppose that script C. Maybe I should say script C. Script C is an ideal of the ring R bar, which is FQ bracket X mod X to the n minus 1. So so again, we're starting off with a cyclic code of length n. So we just said that this is an ideal of this ring R bar. So then, if that's the case, then the script C is actually a principal ideal. Or in other words, C is the set of all multiples. So let me remind you what the recall. Oops, I want to do that. I want to do this. There we go. So recall. In a ring, when we're working in some ring R, the principal ideal parens A, the ideal generated by A is the set of all R multiples of A, i.e. parens A equals the set of all things in the form RA, where little r is in big R. And that notation is kind of invisibly being used here, almost invisibly. So remember, so the parens G of X is really, oops, let me undo that. Be a little bit more careful of that. I don't want to run over. Oh, there we go. I did not run over script C. So this parens G of X refers to all polynomial multiples of some fixed polynomial G of X. So yeah. So anyway, before in the previous theorem we just talked about, we saw that cyclic codes are ideals, but what kind of ideals are they? Well, actually, any ideal of this ring R bar is principal. In other words, it's a set of multiple that has some generated polynomial G of X, such that every element of that principal ideal is a polynomial multiple of G of X. In other words, and furthermore, moreover, we can choose that generator G of X such that G of X divides X to the n minus 1. Right. Yeah, I guess the proof is sort of is done by a bit of a sleight of hand that sort of makes it look relatively natural. So the idea is that ideal of but if you want to get into this, here's the idea. If you want to get into the subtleties of this, and you don't have to, you mostly need to know the result. So the first thing is that we start off by assuming that C is an ideal of R bar, which is, I'll put in the bar in a minute, which is F Q bracket X mod X to the n minus 1. So it's an ideal of this one ring, this quotient ring of F Q bracket X. This is an ideal of R bar. Right. So that's what C is, that's what script C is by definition. But if you go into the details of the proof, that means it corresponds to a different ideal I of FQ bracket X of just polynomials without that mod, and we know that that ideal I must be principal, and why is that? Because any F bracket X, any ring of polynomials, is a PID. I know this is like the most abstract thing we talked about, principal ideal domains, but there it is. It happens to be particularly useful here. So, and in particular, I contains x to the n minus that ideal I contains x to the n minus 1, and so we might as well take our generator G of X to divide x to the n minus 1. All right, okay, so that's the idea of the proof. But anyway, so the point is that the real punchline, the takeaway from this theorem is that every cyclic well, first of all, we already saw that every cyclic code is an ideal of this strange ring R bar. And the second point here is that all such ideals must be principal, generated by a single generated polynomial. And the third thing is that we can always take the generator of that ideal to be a divisor, a factor of x to the n minus 1. Okay, so yeah, so C is principal, and its generator polynomial divides x to the n minus 1. So so the idea of the proof, I mean, I just want to mention the idea of the proof just for those who are interested, but the main point is to understand the statement of this theorem. So are there any questions about the statement of this theorem? That every cyclic code of length n, of course, it corresponds not just to any old ideal, but a principal ideal generated by a divisor of x to the n minus 1. So questions? Okay, so the point is, so here's a definition, but it's really making a point. So let C be a cyclic code. So let script C be a cyclic code of length n over fq. We define the generator polynomial of script C to be the minimal polynomial g of x of script C as shown above. In other words, that means, so if you want to study cyclic code, if you want to study all, right? So so the nice thing about this kind of algebraic-ish theory, not algebraic, the algebraic theory, is that not only does this allow the algebraic theory allow you to study just one cyclic code, it allows you actually to study all possible cyclic codes of length n. All possible. So we can move this around a little bit. So if you want to study all, not just any one particular cyclic code of length n, but if you want to study all possible cyclic codes of length n. So I mean, this is kind of a great thing, right? Like now, it's not just like you want to look at one particular thing. You want to find all possible codes of length 7 or whatever, because you want to make sure you didn't miss anything, because maybe there's something else out there that's even more awesome, say, than the Hamming 7 code. And so maybe let's look at all possible cyclic codes, and the fact that it seems that really more symmetric codes seem to work better. Maybe by looking through those factors of x to the n minus 1, by factoring the single polynomial x to the n minus 1, you can actually sort of list all possible cyclic codes. By factoring that polynomial x to the n minus 1. Using coefficients in FQ, you can list all possible codes of a given length and study all of them. So that's the kind of neat thing about this kind of theory, is that you can just sort of find this. Gives you a recipe about how to find possibly good codes in nature, just by factoring this one magic polynomial. Suddenly you can do great things. But it's sort of like having this magical piece of rock, and that if you break apart the rock, you suddenly obtain every possible element in the world. Wow, I'm like really caught. First, I had like the thing about I don't know. I'm getting really cosmic today. Anyway, okay, so yeah, so let's go ahead and do that. So anyway, and I guess. Yeah, we'll do something a little more concrete before we get back to cosmic stuff. Let's first look at what it means to how to given. So remember, oops, that's not what I wanted. I wanted the pen thingy. So what we showed here is that remember, so what we just showed is that any, oops. I guess make this blue. Any cyclic, didn't quite make that blue there, code has a generator polynomial g of x. So the reason we start off here with a polynomial is that we just showed that if you have if you have a cyclic code, it comes from some generator polynomial dividing x to the n minus 1. So let script C be a cyclic code of length n over fq, some field of order q, and suppose that cyclic code script C is generated by the generator polynomial g of x, where g of x divides x to the n minus 1. And so what this theorem tells you is that the theorem is going to say that the degree of the generator polynomial, oops, if I make this big, polynomial gives you the dimension of the code. So again, the degree of the generator polynomial actually just tells you what the dimension of the code is. That is, if your generator polynomial has degree R, then basically what this say, well, this set of polynomials gives you a basis for script C, and the dimension, but more importantly, perhaps, the dimension of script C is k. K is equal to n minus r. So that is, the higher the degree of your polynomial, the smaller the dimension. Higher degree polynomial is the same as gives you a smaller dimension. All right, so now, proof. Right, what's the first thing you say to have a proof? You want to write the word proof. I should write the word proof there. Okay, so you and I, you folks and I, are going to prove this together. You're going to do the span part, and I'm going to do the linearly independent part. And oh yes, and I've left out a blank space here. So to show that this set here, script B spans script C, that I'm going to leave that up to you. Let me do linearly independent. So suppose g of x, your generator, it looks like c0 plus c1x up through crx to the r. That's what with cr not equal to 0. So that's what it means. So I think I want to make this, well, let me start drawing it. So that means, so if this is your generator g of x, this looks like g of x. This looks like c0, c1, all the way down to cr. And then there's going to be a bunch of zeros here. And there will be n, oops. How many zeros will there be here? There will be n minus k minus 1. So n minus r, sorry. N minus r minus 1 zeros here at the end. Okay, because there are n entries, and there are plus 1 coefficients over here. All right, so now if I take that and I multiply the next column, so all I'm doing here is I'm just doing the thing that you learn how to do to check linear independence in 129A, right? You write out the vectors of your what you hope is your linearly independent set, and in a matrix, and you row reduce it. So I'm just going to do row reduction. There we go. So what's the next vector in our basis? It's x times g of x, right? So this g of x times g of x, all the way down to x to the n minus 1 minus r g of x. So remember, when we multiply g of x by x, that corresponds exactly to a cyclic permutation. So this goes down here. This is cr minus 1. But now that CR sort of moves forward and fills the first 0. fills the space formerly occupied by a 0. Ooh, I know. I should make the zeros a different color. Yeah, I can make it. There, the zeros are green. And the 0 here. Oh yes, that's it. Okay. So and then that means if when I take our next column, which is going to be x squared g of x, then I'm going to get the same thing moved down. CR minus 1, CR. And there's sort of one fewer 0. Again, one fewer 0 at the end here. And so this, how far can this go? Well, there are we observed to start off with that there are n minus r minus 1 zeros down bottom. So you can only fill those zeros n minus r minus 1 times. Fortunately, that's exactly as far as that's exactly the number of multiples of x that we're going to have here. So our last column is going to be x to the n minus r minus 1 times g of x. And so this goes down here. And now this will go down to put c sub r in the very bottom entry. And now we have the situation where all the zeros are now at the top. Oh, this is, this almost makes me, at some point I want to publish this book, our text here. This almost makes me want to put this in color. Though, I have discovered, I just published a book, he said, publicizing himself. Now, and it turns out that if you put stuff, every color page like jacks up the price of the book by a lot. So, if you're going to put color in, there better be some good reason. So I guess this is a pretty good reason here. Anyway, so this is what so that's what our matrix looks like so far. I'm going to let you stare at this and while I sort of fix this. Oops, no, I want an eraser here. While I fix this stuff up here. Oh, great. All right, so that's what, so like I said, this proof of linear independence is going to be, well, I'm going to put everything in it. Oh yeah, so this over here was n minus r parens n minus r minus 1 zeros at the bottom, and now they're sort of moved up to the top by the end. All right, so what happens when you row reduce this thing? When you put this into reduced row echelon form, all of the CRs become ones. You can multiply each column, or you multiply each row by a CR 1 over CR, a CR inverse, and so all the columns, and you use those to wipe out everything above you. So all the columns are leading columns. That implies by chapter 5, or by 129A, except over arbitrary fields, that the initial set, this set of vectors we started off with, is linearly independent. Ta-da! All right, and so let me draw. Yay! Smiley face. Oh, with one square eye. Well, okay. I think that's an appropriate way to, appropriate place to end thus endeth the lesson with a sort of decent multicolored picture and a very, very poorly drawn smiley face. All right, so time's up. And so I think it's definitely time for me to give up. But anyway, so like I said, you will do the other half of this proof in your homework for 8.3. And so I thought I'd do my half. So I think next time, yeah. So next time we'll talk about some concrete matters, talk about encoding and reading cyclic code, and we'll talk about examples, sort of some of the more prominent examples of cyclic codes, they're all ones you've actually seen. Spoiler alert! If you go look at this particular part of the chapter, every code. It turns out that every code that we've seen so far in this class actually happens to be cyclic code. And then on Monday we'll talk about we'll start 8.4 and talk about how to get one particular way to find, not just sort of randomly find good cyclic codes by just trying every possible cyclic code, but actually an organized way to find that guarantees that you have a good cyclic code. Okay, thanks very much, y'all. Thanks, YouTube. Thanks everybody for stopping by, and take care. And and don't forget, there's a problem session on Friday. Please stop by the problem session and take care. Stay safe. Stay at home. Bye.